So we're going to continue our discussion about amino acids and how they react. Amino acids, since they have an amino group and a carboxyl group, they undergo typical acid-base chemistry. The amino group can be protonated to form an NH3, or the COOH carboxyl group can loosen hydrogen to become a COO- or a carboxylate group. Since it can either gain a hydrogen or lose a hydrogen, it's called an amphoteric species. The protonation or deprotonation of amino acids really depends upon their pKa and the pH in which they are around. If the pH is greater than their pKa, then they will be deprotonated. The way I remember that is the greater sign points toward the H, meaning that the H will disappear. If the pH is less than the pKa, it's going to be protonated. And again, the way I remember it is that the less than sign is pointing away from the H, meaning that's going to leave it alone. When you do this, it's important that you look at each functional group separately. For example, if I were given a question asking me to determine the charge on valine, this is valine right here, I would have to look at the carboxyl group and then the amino group right here. So what I would do first is I would look at the carboxyl group. The OH groups on carboxyl groups, their pKa is around 2. And if I were in a pH of 7, the pH is greater than the pKa, so I would deprotonate it, giving it a negative sign or a negative charge. The NH3 has a pKa around 9 or 10. So you would really require a pH much higher than 7 for it to be deprotonated. And in their natural form, they are positive. So you would have a positive charge. So the overall pH or the overall charge on this amino acid would be neutral. And since it's neutral, since it has both a negative and a positive charge, it's called a Zwitter ion. Now, this is the case for most neutral amino acids, but then when you have acidic or basic amino acid groups, which I will mention in a little bit, then you would just do the same procedure over again, but this time you have to take into account their R group as well. You would have to check whether their R group's pKa is less than or equal to the pH. Once again, if it's greater than the pH, then it would be protonated, and if the pH is greater than the pKa, then it would be deprotonated. This leads us into our discussion about PIs. PI is just the pH at which you have a Zwitter ion, which is, once again, when you have both a positive and a negative charge. The PI of a neutral amino acid is simply the pKa of the amino group plus the pKa of the carboxyl group divided by 2. For example, in our valine question from the previous problem, the PI would just be the pKa of the amino group, which is around 9, and the pKa of the OH group, or the carboxyl group, which is around 2. So you would just do 9 plus 2 divided by 2. When you have a charged amino acid, you should be given the pKa of the side group. And under that condition, you would take the two numbers that are closest to each other, add them, and divide it by 2. For example, if I have lysine, which I'll show you the structure for in a second, I would take the amino group, which is a 9, and then its side group has a pKa around 10. You would add them together and divide by 2. The next part is titrations. You can determine the PI of amino acids by performing titrations. This part of the graph is where the pH equals the pKa, indicates that the first hydrogen has come off of the carboxyl group. This area around here is the second half equivalence, which indicates that the H group of the amino group has come off. This part where there is a vertical line is when you have a Zwitter ion, which is basically just a negative and a positive in the same amino acid. And for all neutral amino acids, this is the type of graph that you would see. But if you have a charged amino acid, this graph would be the exact same up to this point, but you would have one more flat area up here indicating the hydrogen coming off of the R group at the pH, wherever it's greater than the pKa. This side represents the pH, and the x-axis represents the amount of OH equivalency you had. I did not draw all of the amino acid groups just because some of them include a lot of rings, and you getting a better idea by looking at it from pictures is going to be much more beneficial than me drawing it. But depending on the class you're in, most professors would like you to know the structure of the amino acids that are groups right here in red. And then they would also probably want you to know the 3-letter abbreviation and the single letter abbreviation. All the red ones up here are neutral amino acids, meaning that they have no charge at pH 7. The amino acids in the green boxes are the charged amino acids. Lysine and arginine are positively charged at physiological pH. Aspartate, glutamate are negatively charged at physiological pH. And then histidine is also positively charged at physiological pH. It is for these 5 amino acids that you would make sure to check your pKa of the side groups in determining your PI. Usually for lysine, arginine, and histidine, you would add the pKa of the side groups plus the pKa of the amino group from the backbone. Whereas for aspartate and glutamate, you would add the pKa of the carboxyl group from the backbone and the pKa for the 2 side groups and divide them by 2.